Good afternoon, Year 12. Hello. I know that I actually haven't got anyone here yet. I'm sorry I'm a little bit late. I'm like 2 minutes late. I know there's going to be lots of people struggling to find the link now, I think. Stop. There you go. Right, let's see if I can get the register up. See how many of you guys show up this afternoon. Bum, 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 bum. Sorry. There we go. Looking for everybody. There we go. Let's see who's the first person here. We're going to be looking at IR today, folks. We're going. For watching. Yes. Bum, 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 bum. Sup, Ivan? How's it going, dude? Yeah, Tenzi's in. Yo, Tenzi. Sup, dude? Everyone's appearing. Hey, Ben. I love that. Hello, boys. Cool. Smashing this out now. Got Ben. Is that Rhea? Did I see Rhea? Got Rhea. Yeah, got Sherlyn. Got Michaela. Got Tenzi. Got Kayun. Got Tenzi, got Sherlyn, got Ivan, got Michaela, got Mika. Who else? Got Emma. Doing well. Keep coming, guys. Keep coming. 7 in. I'm missing Dana, missing Nikita, missing Dat, missing Jasmine. Come on, guys. Come on. Last lesson, we were chatting about infrared. And I've put together some questions that we'll have a look at today. I think I've actually put together a couple of booklets, I think. And I need to attach them to the document. But you guys have, the document has everything on it. They're all there. So, there should be plenty of questions there for you. I'm sorry I haven't hyperlinked in the super booklets yet. But don't worry, they're coming. Just got to find the time. Oh, come on, where are they? Oh, no, going Yorkshire already. Oh, no. Oh, man. Right. Oh, come on. So slow. Okay. Looks like I'm just going to have to crack on. Fish face. I'm getting, by the way, I'm getting ridiculous cabin fever. Hey, Dat's arrived. Yo, Dat. Sup, dude? Jasmine's in. Yes, they're coming slowly. Come on. Come on. Where are we up to? Just missing Nikita and Dana. Come on. Where are you? Come on. I'm assuming they're going to be late. All right. So today's job is we're going to have a look at got a couple of learning objectives from the previous lesson. In fact, really only one. We've only got one proper learning objective that we haven't done yet, and that's the explanation of global warming. Do you know what? I think I can just continue with my my notes from last time. I might do that. Yeah, potentially. Still haven't got Dana. Still missing Dana. Who else am I missing? Who was the other one? Also missing Nikita. Come on. Okay. All right. Done. Moving on. I'll mark him as missing. Where are we? No, not there. Okay. Fine. Okay. Share screen. There we go. Do that. Hello. Right. Okay. Just gonna move that out of the way. There we go. So I'm just gonna get rid of my keyboard. Get rid of my keyboard. Right. Okay. Notes. So last lesson. Oh no, hang on. Just fiddling around with my laptop. Sorry about this. Okay. There we go. So last lesson. We were looking at, this is where we left off. We were doing infrared spectroscopy. Donna. All right, there you go. Has anyone seen Nikita? No. Okay, so this is what we were doing last lesson, and we were doing bond absorbances, and we discussed them and what their shapes were and how cool their shapes were. Like you're always smooth when you're on alcohol, yeah, but then you get the horrible big jaggedy mess. It's still wide. In fact, the carboxylic acid one is wider than the alcohol absorbance, or trough, but the alcohol one's nice and smooth, whereas the carboxylic acid, the OH, is horribly jagged. So we did identifying particular bonds, and now we need to do global warming. So, okay. So I'm going to go down to here. I remember the mess of me not being able to spell cuvette. I've learned that now, though. Yeah. Quvette. Yeah. So now what we're doing is we are looking at, can we put a little subtitle of global whopper? Sorry, warming. I meant warming. Yeah. So global warming. So I don't want to start. I could at this point start drawing, some lovely images of global warming. And the idea here, you've got the sun, and the sun emits all kinds of frequencies of light. But the one, of course, for global warming is infrared. Yeah, it's the IR, which is going to be the one that's problematic. UV, of course, is the one that gives you a suntan. Yeah, also the one that's absorbed by the ozone layer. You probably should have all come across the ozone layer now by now. But IR is the one for global warming, GW. Yeah, and what's happening is when it strikes the Earth's atmosphere. So this, of course, is the Earth. Yeah, there we go. There's the Earth. Should do it in blue. Look, there you go. Bit of. Oh no, I don't want to do that. Hang on, undo. I don't know. So anyway, so there's the Earth, and here's our Nikita. Okay, Nikita. Mark, he was in. There you go. Cool. Nice to see you, Nikita. Good to see you. Nice to see you too, Julian. Glad to see you joined us. So the question is, why is carbon dioxide causing so much trouble? So the reason being is we now realize that the C double bond O, yeah, this bond here is polar. What that means is not potar. I don't know what that is. Potar. I don't know what that is. Polar. It's polar, which means it can absorb infrared radiation. Yeah, and because it can absorb it, what's happening is it's being struck by IR and it's causing it to vibrate more. Yeah, this means that the atmosphere is warming up. Yeah, we're getting hotter. That literally is what's happening here, folks. Yeah, the air is quite literally warming up. Yeah, it's trapping the heat. By the way, you see in physics, they draw pictures like this. Oh, yeah, it's getting trapped inside that. I hate that diagram. It's one of my pet peeves. Really annoys me. It's nothing to do with it acts like a layer and it reflects it back. What? Like, what a load of just physics rubbish right there. No. Yeah, it's not what's happening. The atmosphere is filling up with carbon dioxide molecules, which are absorbing the heat from the sun and are keeping it in the atmosphere. Yeah, that's what's happening here, folks. So the whole air is literally warming up. And then we looked at the absorbances of these particular people. Yeah, we looked at how bad they were. We also looked at, I think, how bad water was. Water is an insanely bad greenhouse gas, but we never talk about it. I wonder whether or not I can find those graphs. I don't think I did actually keep them, did I? I don't even think I even drew them. So we can just compare water vapor. So, by the way, water vapor or steam, either one. So the infrared spectrum of this guy, just going to make my pen a bit thicker. The infrared spectrum of this guy for water, it's like an enormous it's just massive. Yeah, and all of this is what's being absorbed. Yeah, it's massive. It's a huge amount of heat being trapped. But the thing is, though, we don't worry about it because the water doesn't stay in the atmosphere. So we keep putting it up there, but it doesn't matter. It comes back down as rain. It's basically static in terms of its percentage, which means it really doesn't matter. Yeah, we don't have to worry about it so much. But the carbon dioxide, on the other hand, is a real problem. The reason being is the carbon dioxide, of course, is going up into the atmosphere. So CO2 has a rather odd graph. CO2 has a really big fat absorbance like this, and then a few little baby ones. Yeah, it's not nowhere near as bad as water, but the problem is the CO2 is remaining in the atmosphere. Yeah, it's also, its peak is not where it should be. That number that it's hitting here should be hitting. Can anyone remember what the frequency is of the C double bond O peak? I wonder if anybody's been learning them. Not peak, trough, sorry. Can anyone spit me out the value? I wonder how long it's going to take somebody just to spit out that value. I've got a feeling there'll be some people who've been already starting to learn these, and they're really handy to know. I wonder how long. No, nobody, no, still no. Makes me sad. 1750 is where, yeah, oh, that'll do, Ivan. It's actually 1750. That's what it should be. 1750 wave numbers, per centimeter. Weird units too. Yeah, there you go, Tenzi. Nice shout. I like it. Boomer. I don't know what that is. Don't know what that is. So 1750, but it's not. This is now at like 2,200, which is weird. It shouldn't be there. I'm going to show you a question actually regarding that in a minute. But it's quite nice to actually have, like, you guys get battered with this whole thing of global warming, you know, all the time now. It's just part of your society now, because you realize that this is going to have an impact on you guys. And so it's nice to have a bit of a better understanding of what's actually going on here. Other contributors to global warming includes methane. That's another one. But anyway, let's move on. So we kind of looked at this and kind of understanding that these polar bonds and carbon dioxide are the reason why IR is being absorbed, right? So we can then kind of tick off this one. We can kind of go, right, global warming is done. What we now need to do is I want to show you guys some example questions, because it is so easy as a teacher of any subject, you know, to forget what it's like to actually look at exam style questions. I think that it's in my downloads. AS, let's go to book 1. Now, I'm going to post these. Oh, sorry, we couldn't add it. It's already open with another app. Oh, that's weird. I don't know. I don't know. Have I got it open here now? I don't know. Don't I don't know. I don't know what's got it open. Let's try one more time, I guess. Insert PDF. Let's go for book 2 then. Fine. Oh, OneNote. Sorry, we couldn't add a printout of Cube. If you can't open it with another app, there might be something wrong with it. Oh, that sucks. Okay. I don't know what the problem is with that then. That's weird. Okay. That's strange. Maybe it's too big. Maybe. Don't know. All right. So let's go through some questions here, folks. Now, what I need you guys to realize is that when we started this whole idea of analysis, yeah, I spoke to you guys about all of these lot, yeah, analysis, stroke structural determination, and you realize that this whole thing is such an enormous topic, and it's not really separatable. Yeah, it's not like there are going to be these individual questions. They're all kind of merging and melding together. And one of the key things is chemical tests. So let's have a look at these questions. What I'll do is I'll just kind of talk. The problem is I can't write on it now. It's a bit of a nightmare, that. I think it's just because it's too big. It's 45 pages long. That's half a mark scheme, by the way. Don't freak out too much. But it's not going to let me write on it. That's really irritating. I'm going to close that down. See if I can insert it now. That's weird. It's really bizarre. PDF. It's never done this before. Oh no. I didn't really think about where I was actually going to put that. I probably should have put it on a new document. Oh no. It's putting it in now, folks. There we go. Right, give me a sec. Wow, my computer's like, oh, it's so big a file. It is a lot of pages. It's a very big file. That's going to really slow my computer down. Like, big time. Big time. Right. Come on. Come on, little computer. Come on. Come on. It's thinking about it, folks. Sorry about this. Doesn't usually take this long, but as I said, I don't usually insert a file that's kind of this big. It's 45 pages. Probably wasn't the best idea, that. I don't think I really thought this through very well. What I should have done is I should have gone through the thing and just picked out the questions that I wanted. All right, right. It's in, amazingly. I've no idea whether or not I've just gone over the top of all my other files. No, there we go. There it is. Right. So let's have a look. So, number 1, a student was given an unlabeled sample of pentan-1-ol, pent-1-ene, pentanoic acid, and pentanal. Name the reagent that the students should use to identify that the sample is pent-1-ene. Right, guys, everybody, can you please do me a favor? Just I'd like to think that you're all saying it out loud to the laptop. Yeah, I realize I pause it and have a go. I just like, there's no point. I just like to think that you guys all know these things. Let's keep it short and sweet. So we're detecting an alkene. Yeah, the answer is going to, of course, be bromine water. We know this. Yeah, it's going to be orange bromine water. So we're going to have, I'm just going to go for black. So we've got bromine water, Br2 aqueous. I'm shortcutting. I wouldn't write that in reality. I'd actually give the look name. Oh, I can't do it. Bromine water. Yeah, and the observation for the alkene is going to be orange to colorless. We know this. Yeah, nice and easy. Good old chemical tests, not gone away. Next, name the reagent that could be used to identify that the sample was pentanoic acid. This is going to be sodium hydrogen carbonate. Yeah, and we're going to say, name, I'm about to lose it. It's so easy to do, folks. Like, really, really easy to lose those. It specifically says in the question, name. Yeah, so I'm going to go sodium. They'll actually allow sodium carbonate. Can bromine water be brown? No, it won't be. Bromine water is not brown. That would be brown. Is iodine water at high concentrations. Yeah, it's not going to be brown. It's going to be orange. Sodium carbonate would be okay, but I hate that. It's wrong, but the exam boards allow it. It's sodium hydrogen carbonate. Yeah, and we're going to see effervescence. Effervescence. I can't spell effervescence, aka fizzing. Lol. Yeah, we're going to see fizzing for the carbon, for the pentanoic acid, for the carboxylic acid, and we're going to say technically you're going to pass that the bubble gas through lime water, turning cloudy. Name the reagents that could be used to identify pentanal. Oh, okay, that's not too bad either. So pentanal is going to be a new one for you guys, which is Tollens reagent, although Tollens silver mirror observation, but actually Edexcel don't really want you to know that one, but they will allow it, of course. But what they want you to be doing is they want you to say failings, yet not Benedict's, although I think it actually says they allow Benedict's, which is really irritating. Should be failings, and it's going to go from blue to a brick red precipitate. Next, right, here's our first infrared question. The student deduced that the spectrum in this image below was that of pentanal. Justify this deduction and suggest why the spectrum cannot be pentan-1-ol, pentanoic acid, and pent-1-ene. Right, so what we're doing is we're using our little bit of data. So hang on, I'm going to go find my data. They're going to give you your data. Data is on sheet given to you. So, you know, IR data. There you go. Let's go images. Just want simple IR data. So I can't find, just want simple. Give me it simple. Don't make it complicated. Just want, don't make it complicated. No. No. Just want simple data. Can go for any data. Doesn't really matter. It's just simple data. It's easy, isn't it? Let's go for this one. There we go. So we've got compound Z1, Z2. Okay, so it's just giving us the positions of where these peaks are going to be. So we've got a C double bond O. Oh, look, 17. That's oh no, you see, that's complicated data. Given to it more specifically. It's not really what I want. I want simple data. Let's go for that one. How about that? I don't know. Compound. Putting it in compounds. Don't want compounds. Let's go AQA because I know that one's data. That data is easy. Okay, got you. Copy. You'll have a similar. By the way, you'll have a similar picture for yours. So let's just put that on there. Paste. Go on. Just work, will you? Just work. Don't mess with me. It's not. Is it working? Did it work? I don't know if it worked. Oh no. Sorry about this, folks. Hang on. Yeah, it's there now. Winner. Right. So So why is it not pentan 1-ol? No. I went a bit too far. Yeah. No absorption for acid for alcohol. That one there. So I'm going to put no absorption. Yeah, no absorption at 3230 to 3550 OH alcohol. Going to be that specific, folks. Yeah. In the exams, will they ever give us these values? Well, they'll always give you those values, Ria. Always. They come on the back of your periodic table. Do you want to see? I can show you. Let's actually use Excel data. So hang on. A level, IAL, yeah, chemistry, data sheet. It's in your specification. I think it's at the end. Let's try and find it. You guys need to be able to use this anyway, so it's very reasonable for us to actually look at what they give you. It might be at the end. I think it might be at the end. Oh, there we go. Indicators. IR, where's IR? There it is. There we go. There we go. So this is the data you get. So all you're doing is in this particular question, yeah, it says, why can't it be pentan 1-ol? So find the ol group. Where's the OH? There you go. OH vibration of ols and phenols, yeah? And you're going 3750 to 3200, and you're saying it's not there, no absorption. Next, right, next one, pentanoic acid. Oh, pentanoic acid would be like, yeah, it'd be like that. Yeah, this big broad one here. Here's the oic acid one, like that. And you're going to go, no absorption, no ab at, and then you're just going to quote the data. Yeah, you're going to go carboxylic acids, 3003 to 2005. You're going to say no at 3003 to 25. Yeah, OH acid. I've put OL instead of OH. There we go. OH alcohol. Yeah, no peak there. And then you're going to say pentene. Ah, well, that would be a C double bond O. Yeah, so the C double bond O is at 1650. Well, that's not there either. That'd be there. There's your 1650. It ain't there. None of them are there. So you're going to go to your data sheet and you're going to say alkene. There you go. Oh, that's interesting. So the alkene has got 3,950, but hang on a minute. That's not really what we want, is it? It's usually lower. I don't know why it's, hang on a sec, because look at the, it's nice to actually have a look. C double bond is C, 1620 to 1680. And this has given me a different arenes. Hang on a minute, arenes. Isolated, there you go. Isolated alkenes. Yeah, you got to be, that's really stupid. There it is, isolated alkenes. Yeah, so we're saying that they're just going to quote that number in the, so just quote the number and say it's not there. So there's no absorption at 16. That's all good. We're done. Yeah. There's also your four marks. Oh, look. We're also going to say, what the heck's, what's this guy? Yeah. That guy is, there is an absorption. So this is no C double bond C ab at 1675 dash whatever. And then they're saying presence. Yeah. Presence of C double bond O at 1750. And you quote the one off the data sheet. You're done. Yeah, 4 marks. Dead easy. Yeah, and they're on the back of your period tables given to you. Next. So, okay, let's get rid of the rest. I don't need to do all that. So let's zoom out again. So this time, they're continuing with this question. And look, Which of these infrared spectrums could represent a carboxylic acid? I'm done. Look at that. Broad spectrum, which is jagged. I'm finished. That's it. Alcohol. There's an alcohol. Oh, look. 1650. There's an alkene. Anything else? Oh, 1750. C double bond O. Smashed it. Nice one. Oh, there's a question there on NMR. Ignore that, folks. Oh, just ignore that. It's A2. Just ignore it. Next. Oh, ignore it. You haven't done it. Still haven't done it. Sorry, it's picked up another one. There we go. The infrared spectrum in figure 3 are for those 3 different isomers of... Ooh, that's quite big, folks. Yeah, that's quite big. C6H12O2. Wowzer. Okay. Well, T is an alcohol. Instantly. Look at that. It's nice and smooth. Yeah. Straight away, T is an alcohol. Next. Oh, so's U. U's an alcohol as well. Nice one. V is a carboxylic acid. Straight away. Yeah. What's really interesting is this one is that one has that's an OH alcohol absorbance, and it has a C double bond O absorbance too. This is a hydroxy aldehyde or ketone, something like that. This one is just an alcohol. Yeah. And this one's your carboxylic acid, very classic. C double bond O in the carboxylic acid group, and then the OH in the alcohol group. OH in the OH group as well. So it says, identify the functional groups present in isomers, yada, yada, from the table. Oh, that's nice and easy. Identify the groups. So we've got an alcohol. We've got a carbonyl. That's a carbonyl, that, if you can't generally place it as a ketone or aldehyde. Carbonyl. How would you differentiate diol from an alcohol? That's a really good question, Julian. It's going to have a higher boiling point. Remember, you guys do have another type of analysis, which is melting point and boiling point test. Yeah. So, do you know what? I'm tempted just to mention that since you've done it. Can you put a little title of melting point test? So a melting point test, just to say that, and I do have to be very clear on this. There we go, sorry. Melting point test. I'm going to reduce this right down, see how it gets on. Wowzer, look at that, much slower, isn't it? So the melting point test really is a test for purity. Oh, laptop does not like that. Test. Oh, wow, look at that. It's struggling. All right, I have to turn that back up again then. Blimey. Put it right back up. There we go. Maybe not right up. Maybe halfway. Test for purity. Yeah, there we go. So test for purity. Oh, stuff it. I'm just going to crack it out. Test for purity is what a melting point is usually used for. Yeah. You've also got things like boiling point tests, which can be used for identity purposes. But you can use a melting point for determining who you are as well. Would they show difference in absorption on IR? Yes, fingerprint region. Come on, Julian. Oh, Julian, you weren't here for the previous lesson. So the way that you do that, even like different isomers, Julian, will have a different fingerprint region. You wouldn't be able to tell from the main part of the spectrum because they'll still have the same absorption in the same region. Although the diol would have a larger absorption, it would be bigger. But it would be very difficult to tell them apart, really. It probably wouldn't actually. It would be quite easy, but I wouldn't want to second guess. I wouldn't want to guess it. But melting point, just so you know, do you know what? It's kind of a set. Okay. You're going to need to process a melting point. Method. Now, melting point means you've got a solid. Yeah. You've got a white unknown. No, not unknown. Yeah, we're checking purity. Yeah, we've got a white solid. Let's call it aspirin. Yeah, they do like aspirin or paracetamol. Yeah, we've got aspirin. People are going to ask me what aspirin looks like. Aspirin looks like this. OH at the top of it. No, maybe not. carboxylic acid group at the top. I can't, and then I've got a, there you go, that's aspirin. There you go. That's aspirin. And the melting point of aspirin, I'm going to say about 127 degrees Celsius MPT. I'm going to have to look that up now. I've got that number in my head. I don't think it's going to be right. The chances of that being right is slim. Really slim. Let's check anyway. Aspirin melting point. Melting point of aspirin. 135. So close. Oh, there's only 8 degrees out. Go figure, eh? So 135 degrees Celsius. So we're going to take that white solid and we're going to use what's called a capillary tube. This is called a capillary tube. I can't remember if it's a double L or not. Capillary tube. It's a really skinny tube. You're going to seal one end. Seal one end of tube. You're going to seal that using a Bunsen burner. Yeah, you're going to heat up the end of it until it melts and forms a blob. Now, once it's sealed, you're then going to pick up small amount of sample. So you're going to literally just like push it down onto it. You'll just take sample. Yeah, take small sample. Take small sample. But then the problem is it gets stuck in the end. Oh, I've written that one in place. Take small sample and it gets stuck in the end of it. I'll send you a YouTube video of this, by the way. Yeah, because then what you need to do is you need to tap it. Yeah, turn it upside down so that the white solid gets stuck at the end. You flip this whole thing over and then you tap it until eventually, so then you'll tap on surface for solid to reach end of tube end. So what you now have is something that looks a bit like this. You've got this skinny tube, which is sealed at the end, and you've got this white solid down here. It's about that much. Tiny, by the way. This is really, really skinny. This is like 2 to 3 millimeters in diameter. Like, so if I wanted to show you how big this actually was, it looks like that. That's how big this looks. It's tiny. Yeah, really small, but the tube's quite long. But that's all it looks like. And then what you do is you put sample into melting point apparatus. Isn't that funny? Melting point apparatus. Sorry, I don't know what accent that was. I have no idea. Apparatus, and that looks a bit like this. You've got a box. It's got a little window out there, and you put in your sample, and the samples, and there's a little magnifying glass, and next to it is a thermometer. Yeah. So next to that is a thermometer, a therm, and then this is your capillary tube, cap tube. Yeah. And when you look through the window, what you see is you see a little heating mat like this. And then here's your capillary tube sample, which is sealed at the end. Yeah. And then here's your white solid. Yeah. And then you see the thermometer running. The thermometer running next door to it, like that. And what you do is you watch this, and what you do is you simply watch it, put sample into melting point apparatus, and then as it warms up, the temperature increases steadily. The temperature slowly increases, and then you take reading. Take reading on thermometer on therm at the first sign of melting. Yeah, and we've actually got melting point apparatuses, and I actually bought capillary tubes this year. I bought them off Lazada because I couldn't get them through school. It was a nightmare. So I just bought some off Lazada. So we've got everything in order to do this test. And we can't do it because we're stuck at home. What a fiasco. I will send you a YouTube link. It's quite fun to do. But first signs of melting. It suddenly liquefies. Yeah. Common questions. Why does the tube, why so thin? Yeah. Wide tube, so thin. Big surface area, so thin. Yeah, it gives it a big surface area, and it means that the small sample will melt very quickly. Sample melts over a very short range. The range is about 4 degrees, yeah, between start and finish. Proper short, because you've got your solid spread over, and it's got a very big surface area to volume ratio. Yeah. Anyway, next. I'm going to go back to this. Let's go back to our normal questions. So, okay, it then says identify what they are in the data book, yada, yada, yada. Yeah, ignore the ones on NMR. Can't do it. Can't do it. Just keep going. There we go. Explain why determining. There we go. Explain why determining the precise relative molecular mass could be used to distinguish between these two compounds. Guys, that's really clever. Right. Guys, I need to add this into your notes. Can everyone do a little subtitle of high resolution mass spec? High resolution mass spec. So we know that you guys use the periodic table, and you now give all relative atomic masses and molecular masses to 1 decimal place. Well, let's run that on these 4. So we've got carbon at 12.0, hydrogen at 1.0, and oxygen at 16.0. Right, let's do the MR for propanol. So that's going to be 12.0 times 3. Plus, how many? So 3 carbons, 1, 2, 3, 1, 2, 3, 4, 5, 6 hydrogens, plus 6.0, plus, and then we've got 1 oxygen at 16.0. And I get a number for that guy as 58.0. Let's do the next one, shall we? Let's now do prop-2-ene 1-ol. So we've now got 3 carbons, 12.0 times 3, plus 6 hydrogens, so plus 6.0, plus 1 oxygen at 16.0, and I get an MR of 58.0. And I now go butane, 12.0 times 4, plus 10.0, and I get an MR of 58.0. Oh dear me, that is a problem. Yeah, that's a problem. Because they're all exactly the same. So mass spec, we're saying that mass spec. Now we already know that we could use fragmentation in order to determine which one's which. Can be done, can. Yeah, but it's just nice to mention high resolution. Yeah, high resolution is also really handy because we've now got mass specs that give relative atomic masses to like 21 places. It's insane how good our mass specs are now. But if you imagine that carbon is 12.00001. Yeah, we've got hydrogen is 1.001, and we've got oxygen at 15.99815. There we go. Let's just do 58.998. Let's do that. Right. So what I can now do is, using those numbers, and I work out these 3, they actually give me different numbers. Yeah. The only 2 that won't are these guys. These guys will be the same. Let's work them out, shall we? Let's work it out. So I've got propanol, which is 12.00001 plus, times 3 equals plus brackets 1.001 times 6 plus brackets 15.998. And I get, for these guys, I now get 58.00403. But if I do butane, 12.0001 plus, times 4 plus brackets 1.001 times 10, and I get an answer of 58.01004. They are not the same. High resolution mass spec can tell them apart. Yeah, but they can't do the other two. The other two are tricky. These ones we'll have to do on fragmentation. This one will split apart, giving me a peak at 15. This one won't. Can't do it. Just can't give me 15. So there's just going to be a missing peak in a fragmentation for this guy. Isn't that clever? We're going to get quite a lot of that, though. Yeah, we're going to get lots of that splitting around that double bond. Yeah, just nice, clever questions. You can see what they're doing and how it works. Yeah, it's nice to add it to our notes. Okay, next. Now, of course, they give us the infrared. So it says, use the spectrum to identify the compound, state the bond, that is alcohol straight away. There's my alcohol, my smooth peak there. Look how smooth that is. Yeah, so that's an alcohol straight off the bat. Yeah, and there's 1650. There's C double bond C. Look at that. OH alcohol, and that's C double bond C. And I'm done. So it says compound, the enol, prop. Oh, let's name it properly. Prop. Oh, 2 en 1 ol. Like it. Bond used to identify the compound, whichever one you want to choose. Wave number used. We're done. Predict the relative boiling points of the three, and the highest and lowest justify them in terms of intermolecular forces. Oh my God, what an amazing question. Right, folks, pause the video, and I want you to tell me which one of these, in fact, put them in order from highest to lowest, yeah, and then give me the WIMPs, the weak intermolecular forces that are present, yeah. You can describe them, all that jazz. Okay, pause the video, go. Here's your answer. The highest is number 2, the enol. Yeah, the enol is going to have the highest. The reason why is it shows hydrogen bonding, yeah, between the molecules. Hydrogen bonding is much stronger than the DDs in the aldehyde, the propanol. Yeah, the aldehyde is in the middle. Yeah, and that's because it shows DDs, dipole-dipole attractions. Yeah, and then we've got the lowest being butane. Yeah, butane is the lowest because it's only London dispersion forces, LDFs, sorry, or VDWs, either one, whichever one you prefer, VDWs or LDFs, whichever one you want. Yeah. And they're the weakest, yeah? So hydrogen bondings are stronger than dipole-dipole attractions, and dipole-dipole attractions are stronger than van der Waals forces. We're done. Yeah? They're going to ask us to describe how these are present, draw pictures of them. You get the drill. Yeah, you know these are coming. Next. Compound ABC Isomers, the molecular formula of this. They all have an absorption in their infrared spectrum. On the table of the data, identify the bond and the functional group present for this absorption. Right, 3230 to 355. Okay, let's have a look at yours. I'm curious to see what your data table says. What's your data table? What's it say? 3230 to 550. 3230. It's going to be alcohol. 332. It's going to be alcohol probably. OH. Oh, 32. Oh, it's a bit hard to me. It's a bit high. Let's have a look again. 3550. It's very high. 3550. Let's have a look at AQA's Infinite Wisdom and see if their data's similar to yours. Yeah, I bet you it's gonna be OH alcohol probably. Yeah, it's very high up in the. Let's have a look. OH alcohol. There we go. There we go. Not complicated. They're just going to give you their question, folks. It'll match the data. You get used to these questions. You just got to practice them. Let's go to the next one. Let's find the next one. I want to find one of interest. I want to find an interesting question, not boring question. Can't do that. NMR. It's A2. Oh, alcohol, carboxylic acid. Oh, passed it already. Come on. Reagent conditions, that's all good. That's not very hard. Just trying to find one of interest. Alcohol. Oh. So which one's that one going to be? Look at that. 1750, folks. It's aldehyde. Boom. Done. Yeah, 1700, 1750. There you go. Straight away off with the aldehyde. C. Next. Ooh. Ooh. That's interesting. Nobody. Look at that. Nobody out. That's the fingerprint region. Nobody outside that. These are carbon hydrogen bonds. That's weird. Oh. Eh? Dunno. Don't know who that is. It's a weird one. Oh. There's a double bond C. There's a C double bond C, guys. Look at that. Tiny little big. But it's at 1650, that. It's at 1650. That's alkene, that. So number 3, alkene. Where's alkene? D. C. That's going to be D. Next. Alcohol. Straight away. Look at that. You're always smooth on alcohol. Where's my alcohol? There it is. B. Right. So the question is, who's left? C, D, and B are gone. C, D, and B are gone. It's either A or E. Well, okay. Nah. They don't want you to use E. So the answer is A. Lol. Nice one. I thought it would be. But, wasn't entirely sure. Next. Alcohol. Alcohol was an L. Oh. Next. Alcohol with a C double bond C. That's an enol. Love it. Love it. Should be that quick, folks. Oh. Global warming. There's water vapor. There's carbon dioxide. Use the information use the information from the indirect spectrum to deduce one reason why the students conclude that water vapor is a more effective greenhouse gas than carbon dioxide. It has bigger troughs. It is absorbing more frequencies of infrared radiation. We're done. Use your knowledge of the bonds in CO2 that it might not be predicted from the data, might not be right, because we know that in carbon dioxide, the bonds are C double bond O. This should be at 1750. 1750 is here. That's 15. Yeah, 1750 is going to be like 15, 2000. It's going to be like 1750 is going to be like, should be there. And it's not. It's there. It's in the wrong place. It's in the wrong place. Wrong place. Anyway, I'm going to leave it there, folks. We're done. We're finished. Guys, I hate to tell you, but I think, let's just quickly go up and check, because this is your specification. I think we might have just finished, or maybe not, but we'll see. Halogeno, we've done that. Nuke sub, we've done. Alcohols, we've done it. Yeah. And then mass spec and IR. Wow. We're done. Is there anything on fragmentation patterns? There you go. Well, I'll do that a little bit more on that. But guys, I think technically we're done. Wowza. That's exciting. Right, so we now need to do a bit of paper 3. I think that would be a really good idea. What I'm going to do is I'm going to set a paper 3 for some for homework. Can you do me a favor? Let's see if we go. Do you know what? I'm not going to do it now. I should be. Oh, I should be doing it. I'll put it on the classroom. I'll put it on the classroom, guys. All right. Oh my God, we're done. That's there we go, guys. We're done. Can you believe it? Wow. So unit 2 is finished. So guys, I will do some paper 3 stuff. Absolutely. What we need to do is look at some paper 3s and see the kind of practicals that they constantly ask about, make some notes on it, discuss them, do some points. I'll point you in the direction of some YouTube videos. I might even make some myself. If I can get into school, that is. Which I probably can't. But anyway, I will love you guys and leave you. Have a great day. Year 12, it's been great to see you. I'll speak to you soon.